Alright, welcome to lesson 10. Again, it will be a short lesson and we will deal with regularization. Also very important in machine learning. You will be using it all the time, so it's important that you get this concept. Regularization is basically to prevent overfitting. Yeah? It basically simplifies your model. So let's take a look at the cost function in relation to the number of iterations. Every time you iterate and you train the model, your training error will actually come down. That is training error. Training error. Okay? But what you will see is that your test error suddenly will go up. After going down for a while, it will go up. And that is where you start to overfit. Yeah? So, what are the options now? What can we do? Well, one thing we can do is early stopping. Yeah? You could say, well, let me stop here. You do number of iterations to here. The problem is you don't really know when to stop. Why stop here, why not here, and so on. So not so obvious. The second thing we can do, and we do this preferably, is to penalize the model for complexity while we train the model. Yeah? And you've seen this is the housing price prediction cost function, which we call mean squared error, is the sum of all the differences between the real y and the predicted y, and then we squared it. That was the cost function. What we do now is we're gonna add a factor for complexity. Okay? This is what we will do. Basically, we prefer small weights near zero. That's basically what we prefer. So that means that we want to penalize larger weights. Yeah. Now there's two famous regularization techniques. One is the L2 regularization, also called rich regularization. The other one is L1 regularization, also called lasso regularization. Basically, L2 regularization takes your cost function, 1 over m, and then y predict minus y squared, and then it adds lambda times the L2 norm of the weights. Yeah? Remember in linear algebra we've seen that there is an L1 and an L2 norm for a vector. Well, rich regression takes the L2 norm of the vector. So that means that because of the square, every time your weight is above 1, you're going to penalize it because you're going to add factors to it. Yeah? So how to visualize this? Well, if you have an example, for example, and this is y, this is a sum over y. Yeah? If you have only two weights, you will have W1 square plus W2 square. And you see that if this is W1 and this is W2, you have a circle. So you have basically this is your regularization term. And remember, we have still our minimization problem. Yeah, these are the contour lines. Yeah. And what happens is that when lambda is 0, there is no regularization, and the minimum you will aim for is going to be this one, yeah? Because there is no black circles. Now, as lambda starts to increase, yeah. So if lambda is very, very large, let us take this scenario. If lambda is very, very large, this term will not matter. It will all be about this term. Your minimum is going to be here. Yeah, this is if lambda is very, very large, and this is if lambda close to 0. Yeah. So basically, what this term does and what this lambda does, it gives you the flexibility to, have your minimum converge on the line between these two crosses. Yeah.